My pleasure to introduce Doug Call, who's going to be our moderator and chair for this session. Doug's professor of environmental engineering at North Carolina State, so we're in his home turf here. His group focuses on recovering resources, nutrients, and energy from waste using biological and electrochemical techniques. And through the STEP Center that you've been hearing a lot about, his group is working with water resource recovery facilities to understand how biological phosphorus removal processes become unstable and what process control strategies can be used to prevent or minimize unstable behavior. And now, as an operator of a membrane bioreactor myself, I might learn more about this as well. So take it away, Doug.
All right. Thanks, Jim. So just a little bit of background introduction to this session. Really, it's focused on phosphorus removal and recovery as well from wastewater treatment. We're going to dial in primarily focused on the biological phosphorus removal process. And a lot of that is driven by the fact that that process is a low-cost alternative to chemical-based removal of phosphorus and provides really unique opportunities for recovery of phosphorus that chemical precipitation doesn't offer. And then the second part of this is also what's mentioned in the title is that many of the wastewater treatment facilities, not all, but many, will face challenges in operating the biological system. And so we're going to touch a little bit on that as well. All right, so to help kick this off, set a little background on what we're calling EBPR for short, is JB Needling. He has a PhD and also a PE. He's the wastewater technical director for HDR. He's worked on biological phosphorus removal since the 1970s, so a wealth of knowledge. He designed conventional and advanced technologies to reliably achieve less than 0.05 milligrams per liter total phosphorus. So excited to hear about that. Hand it over to you, JB.
Okay, well, thank you, Doug. That was good. Yeah, I've been involved since the 1970s, actually, before it was even known. And I was fortunate because the guy I went to work for was the guy who invented the process. So, and it took him another 15 years to prove why it's actually working. But he was a keen observer, and so that was his big forte, is that he can see things that nobody else can see and make connections that people struggle. Does this work? It does. Okay. So here's what I want to talk about briefly this afternoon. Phosphorus removal versus phosphorus recovery, and then EBPR and phosphorus recovery. But they're all going to kind of mix together because it's, I think I had 20 minutes or so. And so that's what we'll talk about. So thinking about removal versus recovery, the big difference between them. Removal means just we're going to take it away. So remove it from the wastewater so you can discharge into the treatment plant. That's where we want to meet these limits, which are sometimes very, very low. 0.05 is one that we designed, one of the smaller plants, Coeur d'Alene, needed to meet 0.05 milligram per liter, and we do it through not biological in that case because they have treating filters, chemical addition, and chemical polishing. And so, but that's another topic for another day. The phosphorus that is removed, as you know, the only way you can remove it is biological. Particulate. There's no gaseous form of it that's really meaningful, and so it goes to landfill, compost, land application, places like that. Phosphorus recovery, on the other hand, is to recover the phosphorus and then make a useful product out of that. So let's talk about that a little bit. First, I want to talk about just the phosphorus removal part. Show you here a graphic. This is a Neisser stain, and it shows the polyphosphate granules. That's kind of the trademark for anyone who wants to do it. Those granules are very useful also, not only that they retain phosphorus, but it weighs down the flock a little bit. so it settles better and you get better performance out of your treatment plant. The application of the process is to take the biology through an anaerobic phase and an aerobic phase, a phase where there's no oxygen and a phase when there's plenty of oxygen. And then you see this little dance that's happening with the organisms, that during anaerobic conditions, the soluble phosphorus will go up and increase, and volatile fatty acids or readily degradable organics will go down. And then those are stored, and then in the aerobic phase, the process reverses, and the phosphorus uptake is now greater than it was before, and you rebuild the polyphosphates at the same time for that to be used in the cycle. And so one of my friends, Trina McMahon, came up with a biochemical representation of this, and this shows, is there a pointer on this thing?
Yes, top one.
The top one. And it shows basically the key things that I want to point out on this diagram. And that is that as phosphates are taken up, it takes up the organics in this in the second phase actually, and store it in PHBs. But in that process, they release phosphate and the magnesium. And then the opposite happened in the anaerobic phase, in the aerobic phase, where the phosphate is taken up with magnesium to build the polyp again, and then you have a balanced process. But the key thing here is that there's plenty of ammonia around in the area, and then you release phosphate and you release magnesium, and that's the building blocks with potassium for ammonia and potassium and phosphate for building struvite. And we'll talk about that in detail in just a few minutes. So in practice, it looks pretty simple. You have an anaerobic phase in your reactor and an aerobic phase. And so the flow is just down and then through the water and out. And then you see a second train and a third train at the end of this. And so it's pretty easy to establish. When James actually discovered this thing the first time was during a thunderstorm at a plant in Johannesburg. And the lightning took out the surface aerators in the first zone and created an anaerobic zone. And then they saw where the phosphorus went down. And said, why did the phosphorus went down? And so it was all experimental. And then he had another pilot plant that he was running that showed the same result. Just to show a couple of other plants, here is a Empire. This is in Minneapolis. A straight through design that we created with anaerobic zone up front, and then aerated zone and internal RAS recycle. And this is just a picture of what the plant looks like. And this is the startup. I just placed this in to give you a sense for how quick the process started up. The arrow is when we started, and about, 2 weeks later, it went down and remained very flat. So the project, once the process takes on, it's pretty stable. Clean Water Services in Oregon is another one. In this case, there's an extra twist. This is the anaerobic zone. This is anoxic, aerobic. Anoxic is where you have nitrate, and the nitrate will act similar to oxygen. In other words, the uptake will actually start here at the end of the anaerobic zone. So you get release in the red zone, and then it starts uptake, and then it takes up completely in the rest of the aerobic zones. And here's a picture of it showing the unaerated zones, anaerobic, anoxic, and then aerated in the background that you can see. The Durham plant was very interesting because they only had to meet the limit 6 months out of the year. So they had a peak flow of 140 and an average flow of about 15. So you can see huge differences. And so in winter, they didn't have to meet it. And so now you can see what happened with the phosphorus incoming around 7. It's a log scale. And then effluent in summer, it's very low, and in winter, it goes up. So they flip-flop the process completely between summer and winter, and it worked well for them. Okay, some of the challenges that we've seen with EBPR associated, and focus basically on a couple of items, and I'm just going to pick on two of them. One of them is struvite, and this is now a struvite that forms in the plant accidentally. And you can see the problem with it is that you find this crystal growth on equipment. And it'll happen on propellers, it'll happen on pumps, it'll happen in the pipes, anywhere where you exceed the solubility product. The second problem is dewaterability. So just to dig a little deeper, this shows you the magnesium ammonium phosphate, and these are our pictures from that plant, that Durham plant actually. They had a huge problem, and that was then after a successful BioP operation, we found out, well, there's another problem. How can we overcome this? So I don't need to explain. We had a pilot study in Sacramento that we took effluent also, pumped it through a pipeline. Within 2 weeks, the whole pipe was clogged with struvite from a little different scenario, but similar outcome as this. It's just the struvite is a devil. And so there's a few solutions, and I just list two of them, three of them here. The one is to build on the chemistry, and I would say the simplest, if you can do it. Usually it comes in dewatering. When the dewatering reject water from dewatering process comes back, it's very high in ammonia from the breakdown. It's high in phosphate that was released in the digester, and then potassium as part of the magnesium comes back also at the same time. And so then you find yourself in the red zone here. So the quickest and easiest way to resolve that is to dilute it. So if you're in a pinch and you need to know what to do, dilute the water, because then you drive the concentrations below the precipitation point. Now you cannot always do it because pipes, may not have the water, may not have that. You can try and lower the pH with some chemical addition or carbon dioxide injection into a pipe. And then there's commercial proprietary chemicals that is used. There was one electrochemical, a magnetic type device that was on the market for a while. I've never worked with it. I haven't seen it. I looked at it and I wish I had it, but I haven't been able to test it. So I don't know if it works. So I'm a kind of a show me guy. The second problem that we've encountered is the impact of BioP on dewaterability. And that came as a surprise. This was actually noted at that Minneapolis plant I showed you results from. They were very happy with the phosphorus. And then they called us up and they said, our phosphate, our dewaterability just dropped 3 percentage points. And you can see this is, I'm not even sure this is the Minneapolis data, but this is exactly what happens. You can see that deterioration. And, how accidents happen. We saw it in Minneapolis. Then I got a call from Hampton Roads. We were working there. Said, hey, we have this, actually it was an ocean outfall plant, and they didn't even want to do BioP, because they didn't have to, but they wanted this anaerobic selector. And so the anaerobic selector acted as BioP, did the whole dance for them. And so they started seeing poor dewaterability also. And then there was a third plant in Denver that saw the same thing. And so it came all together. I don't know why, but anyway, rotation of the earth, I don't know. But so this was a big problem. And in Denver's case, it actually impacted the viability of doing BioP in terms of the extra cost to truck the solids off. So 3 percentage points was killing them. There's many theories that has been blowing around for this. Mario Benisch, my colleague, strong connections to Germany, and there's a lady there that did a lot of work on this. I forgot her name now. But their conclusion was that it's the phosphate that's creating the problem. And I don't understand the mechanism, but that's what they say. The other one is Matt Higgins has been working on the monovalent, divalent impact on dewaterability in general, and he found very strong correlation between that. The higher the valence, the better the dewatering. And so that's the line that he shows. And both of them showed good correlation. Oh, yeah, I can see there's a correlation. I don't know exactly what it is, but it's beneficial if you can remove the phosphate. And so in general, I would say, if you can remove the phosphorus, whatever strategy you can do, because usually if you precipitate the phosphorus out, you're adding chemicals, so you change the monodivalent composition, and you remove the phosphate that's in solution. So it works both ways. All right. So in conclusion, the issue is struvite recovery is very attractive. It's like controlled precipitation and harvesting the phosphorus crystals to move from problems into solutions. So every time we went into a treatment plant, if you reduce the phosphate, if you reduce that recycle by recovering it, because the recovery goes off the dewatering centrate most of the time, all the time, basically. And then if you do that, you reduce the amount of phosphate that the bugs have to take up in the mainstream. And that's where the big benefit comes in the performance. So you will see performance improvement of the EBPR as a result of implementing the struvite recovery or the harvesting of phosphorus to break that cycle to come back. For one of the treatment plants, we were visiting them. We did the mass balance to see just how much phosphorus is coming back. The biggest recycle I've ever seen, 97%. 97%. That's doubling the amount of phosphate that needs to now be removed a second time around. And that was just a phosphorus, no nitrogen removal plant at the time. So now they've changed also. But yeah, so the solution for them, we suggested to them to just take a little chemical and add it to the recycle flow to tie up the phosphate, reduce the load, and that helped them a lot. But yeah, 97%. Okay, so enhanced biological phosphorus removal require conditions that will give you, that will grow the PAOs, readily biodegradable organics, sequential exposure between anaerobic and aerobic conditions. And there's many conditions. I showed you a few flow diagrams. There's more than you can shake a stick at, and more coming up as time goes by, as we learn more and more and more about side stream, tetrasphere, and all of that. To improve performance, what you want to do, what I have found anyway, is limit the variation of the growth conditions. And what I mean by that is steady operation is a big benefit. I call it don't kick the bucket. And what I mean by that is another story is that for Clean Water Services, at one point they had an incident where there was a connection that brought the reject WAS thickened flow back into the plant, and someone changed the wrong valve and it sent the flow into the primary clarifier. And so the WAS went into the primary clarifier, immediately released a huge amount of phosphorus, so much so that the effluent phosphorus was bigger than the influent phosphorus. Now they fixed it very quickly, but it just showed the instability, and then the whole process took a couple of weeks to recover completely. So cost savings, there's some cost savings associated by recovering that we talked about. So if you take the phosphorus away, you need less coagulants to be added. You reduce the amount of alkalinity you have to add. Cake hauling, because it helps with you recover the dewaterability of it. Reduce dewatering polymer. The big one is reduce the struvite mitigation. And then it'll also help with agronomic loading rates if you're in a state like in Colorado. And then there's the prospect of some revenue sales. So I think that's as far as I'll go. Okay.
Any questions?
Any questions? Yes.
So, the main challenge behind the phosphate removal to use is the heavy metals in the wastewater. So, how do you remove the heavy metals from the strobite?
How do you remove the heavy metals from the struvite? Well, I'm not sure which metal is going to be the most offending in the heavy metal arrays, because the struvite is just pure ammonium, phosphate, and magnesium. So magnesium is the only one that's really going to be. And I don't know if the Ostara,
Yeah, they're here.
they're here.
Happy to tell you how pure their product is.
Yeah.
But the heavy metals bind to the biosolids. Not really the chocolate.
Yeah. So the struvite is clean, or can be clean. I should say can be clean, but because I was telling him that yeah, there's sometimes that I have another project that uses a different device for struvite recovery that's not as clean. Yeah.
Is there any other issues regarding the provide except like using a slow release fertilizer?
Yes.
Is there any other applications?
Oh yes. The actually interesting. So I'll tell you a little story. Yeah, I'm full of stories. The when Ostara built the first big recovery plant, clean water service in Oregon, and my colleague Dave Clark was there at the opening, the grand opening, and actually that is was the centerpiece, that little building there of celebration. But so he went to Ostara and asked them. He said, "What are you going to do with the product?" And the response that he got was, "Well, it's funny you ask, but we're shipping it up to Canada to put into cold water streams to fertilize the rivers." Yeah. So this was rivers that needed some nutrient supplement to manage the ecosystem. Don't ask me why
Bigger.
yeah, I don't understand. I don't, yeah.
It's the loop. Just the loop.
But the slow, I think the slow release was one of the key features of that particular product, is that they were able to dose it, and then because then yeah, they had heavy sacks that they shipped up. Other question? All right.
Maybe one more time. Okay. Moving along now to a wastewater facility perspective on this whole issue is we've got Tom Salon. He's worked with Renewable Water Resources, or REWA, for 3 years. He currently manages the process optimization and planning department within operations. That group is responsible for operations technical support along with equipment rehabilitation. Prior to that role, Tom served as a process engineer supporting RERA's 9 water resource recovery facilities through troubleshooting, training, and pilot study design. After graduating with a master's in environmental engineering, it's a good degree, from Clemson University. Tom.
Sweet, thank you. You notice from that bio, I have not been working on EBPR since the 70s, so take what I have with a grain of salt. No, so I'm kind of here to share mainly about the utility perspective. Yeah, so I'm going to be talking about not just recovering phosphorus, But really, what does it look like for an operations utility that has a phosphorus limit? How do we improve the efficiency and resiliency of the EBPR processes, but also the processes that surround EBPR that we might use if EBPR is unstable? And so I'm going to give a little bit of context on phosphorus removal in wastewater treatment facilities, some of the mechanisms we use. We'll probably go over that pretty quickly because I think we'll all be on the same page about that. And then talk specifically about Malden Road, the treatment site that we'll be talking about today. Some operational improvements that we identified and kind of used to optimize treatment. And then talk about some dewatering and capital projects moving forward and what we're doing to mitigate that increased recycle rate. So the first thing I want to talk about is just general high-level overview of wastewater treatment and phosphorus removal. So I think I saw this similar slide earlier on Doug's presentation. You know, in domestic wastewater, there's total phosphorus and there's three major forms of phosphorus that come into the facility. Orthophosphate, organic phosphate, and inorganic phosphate or phosphorus. And so what's interesting about orthophosphate is it's soluble. And these two are generally insoluble. And so the challenge with removing soluble contaminants from domestic wastewater is we cannot use any physical separation process to remove these. So in wastewater treatment, you know, we use things like filters or settling to basically remove contaminants that we don't want when they're insoluble. But for soluble contaminants, we need a way to make them insoluble so we can remove them with a physical unit process. And so 50 to 70% of the phosphorus that comes in the facility is in the form of orthophosphate. And so wastewater treatment plants have to figure out how to transform orthophosphate into one of these two forms so that we can remove it physically. Because if we haven't done that, we can't get it out. And so we have a couple strategies to do that. So one that we've talked a lot about with struvite is really just chemical coagulation. So pretty simple. Phosphorus or orthophosphate is an anion, and we can add metal salt cations and basically make the product insoluble. We make that inorganic form of phosphorus, and we can remove it with a physical process, whether that's a filter or sedimentation in the facility. So the other strategy is what you were just talking about is the biological process. And this is basically a simplified version of the metabolic pathway JB had up before. But basically what we do to facilitate these organisms is we alternate their metabolic conditions. So we alternate them between an anaerobic condition and an oxic condition where oxygen is present. And it creates an incentive for these organisms to figure out how to grab the metabolites and the substrate in that anaerobic phase. And so the way that they do this is they have this polyphosphate storage, and they can get energy from that and basically store really simple compounds in the cells so they can consume them later. And then when we go back, that's in the anaerobic zone. When we go into the aerobic zone, they're incentivized to build that polyphosphate store up, and then they consume that energy to do more cell growth. And so by doing this cycling, we're kind of encouraging these organisms to build up this phosphorus store for when they're going to need to use it to capture more food again. And so we can kind of create this in the treatment facility to basically facilitate phosphorus removal. And so this is kind of an overview. So I want to talk about that's kind of the main treatment strategies. I didn't talk about assimilation of just biomass growth, but I want to spend some time talking about Malden Road. So these are the major unit processes at Malden Road. So we have influent coming in, and we have our side stream that's like kind of the plant drain. And then our first unit processes, we're going through screening and grit removal. That's mainly just to protect equipment and remove grit. We have primary clarification at Malden Road. We're just removing settleable and floatable solids out of a primary clarifier. We have an activated sludge process with basically an A2O and a secondary clarification. And And then we have deep sand bed filters that go to UV disinfection. So that's kind of a high level overview of the facility, of the liquid train, the solid train, the primary solids, and the wasted activated sludge both go to anaerobic digestion. And then we currently land apply liquid biosolids that are stabilized out of the anaerobic digestion process using thickening, but we are transitioning to dewatering with centrifuges. So that'll be kind of part of one of the optimization things that I talk about. But right now that post digester centrate, which has the high P loading, goes back to the head of the plant. And so this is kind of an overview of the treatment site. Don't really need to go too in detail of this in terms of the major unit processes, but what is valuable for you guys to see is how our secondary treatment system is set up. So this is that A2O process I was talking about. So it's actually really similar to the one that you showed that had the serpentine shape. We basically come in on one side and we have an anaerobic zone and an anoxic zone, and then we go to an oxic zone for all of that. So that's where how we're actually getting those cycling of the metabolic conditions in the field is really these different tanks in series in the secondary treatment process. And so this is a little overview just on the performance of Malden Road. So the facility is permitted for 29 MGD. We have a 1.3 monthly average phosphorus limit. So, some facilities are down to 0.05, 0.12, 0.2. It's a pretty relaxed permit for phosphorus, but EBPR is unstable and we have a kind of a lower carbon source. So as you can see on this axis, this is 2023 and 2024 monthly average phosphorus. There are months, there was one month we were at 1.1, 1.08, but this facility has not had a violation in 20 years, and it is sampled 7 days a week. And so we do not have a TN limit. We are on monitor and report, but it could be added one day. And so some average daily flows in 2024, we were at 18.6 for influent flow. TP was around 0.54, TN 12.03. I'd say some of the biggest challenges this facility faces, we're transitioning to cake application over the next 2 to 3 years. So we're going to be really increasing that recycle load. Really high just seasonal variation in the performance of EBPR. So you can see some of those blue lines. In 2023, we had pretty high effluent phosphorus in the wintertime, maybe a little higher in the summer here, but really just a lot of seasonal variation in the performance. And then our NPDES is currently under review, so we could have a lot lower limits in the near future. So how do we remove phosphorus at this facility? So I just want to go over some free options, air quotes free, how we can remove phosphorus. So the first major step is we just remove anything that settles in primary clarification. So that is actually free. And so we're removing like 5 to 10% in primary clarification. And then we are just from biomass growth, we're removing another, say 10 to 20% just by growing microorganisms. They need phosphorus just like we do, so they consume it in their cells. And then we're getting enhanced biological phosphorus removal just by the setup of the aeration tank. And that's kind of free. Obviously, we have to aerate and things like that, but it's much cheaper than chemical addition. So these are the processes we rely on day in and day out if there is no upset condition. But in the event that occurs frequently, this might not get us below our 1.3 target for performance. And so we have these not free or expensive ways to remove phosphorus through the process. So the first one, we can add carbon right upstream of the secondary treatment process. Carbon is probably the most important part for biological phosphorus removal, so we can add carbon there. We can add alum to secondary treatment effluent from the clarifiers, and we can add ferric to the primary clarifiers to basically improve the amount of phosphorus that settles out in the primary clarifiers. So what I kind of want to go over is just some optimization projects and some things that we've worked on with the operators to basically optimize all of these backup processes. So we've focused on EBPR, but we really wanted to go through a process of how do we make sure these backup processes are working the most optimally as possible so that when we do need to use them, we are ready and can do it as effectively as possible. So the first one I want to talk about is primary clarifier operation. Primary clarifier is not the most attractive part of the treatment plant, but it actually turns out it has a really, really big effect on EBPR specifically. So primary clarifiers, when this is filled and operating, there will be a blanket of primary solids in the bottom of this clarifier. And so one lever operators control is how deep that blanket is. And so if you operate at a really deep blanket, you're essentially holding those solids in the clarifier, and they have a long retention time in that clarifier. So we had an upset one day, and I was out at the plant with the supervisor. We were trying to understand what was happening, and he just mentioned to me, hey, one of the operators the other day set the primary solids pump to the wrong setting and totally drew the blanket out of the primary clarifier, and that was like 2 or 3 days before we had an upset. So that kind of triggered me to go back and say, oh, well, let me see if I can figure out how to correlate primary clarifier blanket depth to EBPR performance. And lo and behold, we found a really, really nice trend. So on the x-axis, we have the blanket depth in that primary clarifier, and the y-axis, we basically have secondary effluent PO4. So what that's showing is at low blanket depths, we had consistently more poor EBPR performance. And as the blanket in the primary clarifier increases, we saw EBPR was much, much more stable. And so what did we do with this information? We set a minimum blanket depth of 18 inches for the operators. So we worked with the staff and said, hey, if you keep this above 18 inches or 20 inches, your EBPR is going to be significantly more stable. And we have seen that it's improved the performance of the system. So another kind of optimization strategy that we kind of wanted to tackle was when EBPR is upset, we'll add alum to the secondary clarifier effluent before the filters. And we wanted to improve the performance of this process. So the first thing that we did was we conducted jar testing on our secondary clarifier effluent. And this was the results we found. So the x-axis is metal dose to initial P. So that's how much alum we're adding related to how much phosphorus is in there. And it's on mole to mole. So stoichiometrically, 1 is really the value for the reaction, but there's competing ions in there, so you need to add above that. And then final P concentration. So that's what we're able to get it down to. So if you notice, we're trying to get below that 1.3. So theoretically, we would need to be in a 3 to 3.5 range. Well, what we noticed, and this is a pretty blurry picture, when we started this, we were feeding, in chemical phosphorus removal, there's 2 really important metrics. There's mixing and there's residence time. We were feeding the alum at the top of the clarifier launder, which is on the residence time side. We wanted a really long residence time. And we talked to some people and said, well, maybe you should trial improving the mixing side. And so we did a trial to change the feed point to right at the launder block box where the flow overflows to the filters. And it's really, really turbulent right there. And we were actually able to drastically improve the metal dose required for phosphorus removal. So this is right here. These are before we changed the dose location, and this is after. So you can see we're getting a similar phosphorus removal with a little, kind of close to half of the metal dose required. And all that was just shifting a hose downstream. And so this was a really exciting test because the system reacts a lot faster now, and so the operators are able to fine tune and control how this operates. And the last area that I want to highlight is carbon addition. So we receive juice waste and kind of high COD content waste from some local manufacturers. And before, we just dumped it into our influent. We didn't have any control over it. We would just put it in the EQ, we put it in the influent. It was just this slug load that went through the process. Well, we actually did a capital project to rehab a tank and put flow meters on the juice and actually had metering pumps on the juice. And we've actually created a system where we can feed this in a controlled state. And so this goes right into our primary clarifier effluent. And so we've started, what the operators have started to do is this phosphorus tracking system where they measure the effluent phosphorus every single day. And if the phosphorus is above 0.5, the operation staff know we need to turn juice waste on. And then if the phosphorus remains high the next day, we need to turn alum on. So by working with the staff, we were able to create this kind of like resilient backup process, and really kind of optimize our resiliency to when we do have EBPR upsets. And so some future projects, we want to get more beneficial waste, but we need to develop a process to field these wastes. So not every waste is going to help EBPR. So we're developing a process to basically run some testing and then understand, could this waste be beneficial to EBPR? We're looking into integrating solids fermentation into that juice tank. So if we had that juice tank, what happens if we just add primary solids to that juice tank? You know, do we supercharge the fermentation of the juice and the primary solids? And then finally, Doug will speak a lot about some microbial work that was done. We really want to optimize our operation based on some microbial upset data that we got from NC State to understand what's actually happening to the microorganisms when we are in an upset scenario. So Doug will share a little bit more about that. So that's some like future studies we want to do from just operations standpoint. But then one final piece that's a really, really big deal for us right now is this thickening and dewatering piece. As we transition to thickening, or from thickening to dewatering, we really want to make sure we're not going to overload our secondary treatment system and not just constantly have to feed alum or look for expensive backup. So we're working with Hazen to build a dynamic biowind model to model the effect of centrate loading on the plant. And so we did a study where we monitored, we set out a discrete sampler and we got phosphorus concentration at the influent when we were running the thickening and the belt presses that we have on site. And you can see we're going from, 5 high 4% or milligrams per liter P all the way up to 20 in the middle of the day, just from operating those thickening and dewatering processes. So you can see this is a really, really high change in loading. And so we're trying to work with Hazen to better understand, does an EQ tank for this process, is that going to help the loading? Is that going to help us mitigate this risk? Do we need centrate treatment? Things like Ro will talk about. Or do we just do nothing? And maybe that loading, the system can handle that. We have a 1.3 milligram per liter average for the month, right? So if you're over a couple days, under a couple days, maybe you don't need to do anything. That's a really big kind of next step for us. And really some kind of final thoughts on EBPR is it's the least one-size-fits-all technology that I could think of. There's so many different factors, from how your centrate comes back into your facility, the characterization of your influent, how much carbon you have. And so it really requires a hand-in-hand operations and engineering mindset to really optimize these processes. Because there's so much variability going on within the facility compared to just textbook BOD to P ratios required for EBPR. So there's a lot of characterization that's like really, really important. And then I think optimizing all P removal processes. It's easy to just focus on EBPR, but I mean, just moving our alum dose point was able to reduce their chemical usage by half potentially. And then really leveraging creative solutions, looking at external carbon fermentation. Those are things that can be low capital options and can really move the needle significantly. So don't, some process like nitrification, it's like you have these simple, like you got to fit in this box, you got to have this SRT. EBPR, there's a lot of different options out there to get to move the needle. And so it's important to consider those. So that is all that I have. So thank you guys. Yeah.
So it was a really great you do with the aluminum phosphate. You're
Yeah.
loading the alum and you're getting aluminum phosphate. As far as I know,
Yeah.
there is no really use of aluminum phosphate.
Yeah, of course. So it basically goes into those deep sand bed filters, and then those deep sand bed filters have a backwash cycle, and that's being backwashed back to the head of the plant. That's going to our primary clarifier, which then settles and goes to the digester. So one day it will go out as biosolids. How long that takes to like that tail, I have no idea, but it's essentially getting turned into biosolids.
And also another question. So does this technology also recover the organic phosphorus that you're talking about?
Yeah, so I would say organic phosphorus is really making its way back to the digestion process. Like thinking of that primary clarifier, that's removing settable and floatable solids. And so a lot of that organic phosphorus could be removed in primary clarification because it's insoluble and it's locked up in those primary solids. And so some of that organic phosphorus is being broken down in digestion and getting turned into orthophosphate and then might be removed in the GBT just by like a liquid separation process. But some of it's remaining in the biosolids as organic phosphorus just for the biomass growth. But the yield's pretty low in digestion, so a lot of it's getting turned into orthophosphate in the digestion process. Yeah.
Great talk.
Thanks.
I'm wondering if you know which type of microorganism that are involved, like to make that biophosphate.
Yeah, so I'll let Doug speak on that. But I mean, there's a lot of debate in that field of who the main player is, and it depends on the carbon source. Yeah, it depends on a lot of factors, but really, Accumulobacter is a really prominent one, and then Tetrasphaera is like kind of confusing. So I'll kind of let you talk more about that.
Yeah, stick around for the after the break because I'll talk all about this. But we actually work with their facility, and the big ones there were the Accumulobacter.
Yeah.
We saw some Azonexus, but it was primarily Accumulobacter in this facility.
Yeah.
No, I just want to make a comment on what he was asking about the chemical solids.
Yeah, of course.
One of the things that we've learned is that if you have chemical phosphorus removal by adding alum, the alum solid has a residual capacity to remove phosphorus. So
Yeah.
if you recycle the backwash, for example, to the head of the plant, it'll absorb some of the phosphate. So
I understand.
it'll actually reduce the phosphorus loading on the plant.
Yeah.
With the chemical slides.
Yeah.
So it's kind of a hidden thing as
Yeah.
well. But we wrote a bunch of papers about that topic.
That's interesting.
FYI.
Any other questions?
I had a question. So
Yeah.
you currently do dewatering? Is that
Yeah, this is a good question. So we have belt presses, but they were quasi abandoned, and we've rehabbed 2 of them just for when the fields are wet and we can't land apply. So they're kind of not able to handle most of the capacity, but they are there. So we just ran them.
so that data is reflective of when they're operational, but they aren't always operational.
Yeah, so you're talking about the discrete sampling.
Yeah.
Yeah, so that was, we actually ran both the belt presses and the thickener to try and get like a total centrate.
Gotcha.
load,
Get a sense of
but
it.
it wasn't like a normal operation.
Okay.
But it's very high.
Yeah, that really increased your load.
Yeah.
Great talk, guys.
Unless someone else has a question. Just a clarification question.
Yeah.
Well, on the tests that you showed where you did the chemical testing,
Yeah, let me see if I can pull it up.
I was just, my question is, that one or the other one. I was just curious, when you did I'm presuming you did jar testing.
Yeah, so the blue line is the jar test.
Yeah.
And then the X's are like the field values.
And my question is, when you did the jar test analysis, did you filter the sample?
Yes. And yes, I had to think the reason we filtered it was because we felt like we are going to be passing this through our deep sand bed filters. So to mimic the process downstream, we should filter it.
Yeah. Okay, good. Just the reason why I ask is we did a lot of tests on jar testing for primary. We did this to primaries. It was a treating filter plant.
Okay.
So,
Yeah.
And we did the jar test.
Yep.
And he didn't follow the pattern at all.
Okay.
The phosphate stayed high. You go 1-to-1 mole ratio, we didn't filter the sample.
Okay.
And so if you filter the sample, then suddenly it went down. And the reason, my explanation is that if you do not, the flocule, because there's little flocks that's still floating around, it's all chemical flocks.
Oh, you can see them. Yeah.
You can see them. And
Yeah.
you take the sample, you put it in the analyzer. In the reagent that you're adding, it dissolves, my theories, it dissolves the phosphate and it show up as orthophosphate.
Yeah.
So it goes into it as a chemical precipitant. It dissolves in the test.
Yeah.
And you measure it.
Okay, that makes sense.
Yeah. So just because I thought, well, because it'll make your curve steeper.
Yeah. Oh, I understand. Like you'd see better. It shifted to the left.
Better removals.
Yeah.
Yeah.
But we did filter
it. If you did filter it, then
yeah, we did filter it. Took me a second to remember that.
I was asked by a lab director once, do we have to filter this? And I said, no, I don't think so. And then later I eat my words.
Yep. Yep. Cool.
Final question?
Oh, I have one.
Yes.
Are you thinking about peer recovery now that obviously for your current layout, it doesn't make sense because you're doing land application, but once you start dealing with that centrate load, is one of the options that you're going to be modeling actual digestate recovery?
Yeah, so it really, for us, it goes back to the economics of like looking at like the chemical costs compared to like the recovery payback.
Yeah.
And so it just depends. It depends on a lot of things of like what our TP limit goes to. Like if we went to a 0.12 or a 0.03, it would 100% be on the table. But it's kind of like you want to see if you can get it out without that consistently before you invest in that capital.
Yeah.
And we have a lot of potential plant expansions coming up. And so capital's kind of tight. So say like, we're going to set aside 15 million for a recovery system when we need a new influent pump station at this plant and we need, to rehab the blowers in this facility. It's like, it really has to have that economic driver.
Yeah.
So we are considering it, but I think it's a lower option to see how we can perform without it. Yeah. Which I'm sure you'll talk about.
The primer.
Yeah.
Perfect segue to the next slide. All right. Well, we have let's take time one more time. We get recovery systems from wastewater and bioprocessing facilities, kinetic process modeling and system analysis, and electrochemical separations with energy storage materials. Dr. Cusick has received several honors for the research related to resource recovery, including the prestigious NSF Career Award. So with that, hand it over to Rob.
Thanks, Doug. Hey, everyone. So thanks for sticking around, fitting out quickly. So my talk is going to really continue the theme that we've been seeing for the first two talks is, you know, at wastewater treatment plants that are transitioning to biological phosphorus removal, then there's this opportunity to recover phosphorus from these side streams that become really concentrated with phosphorus. So because this is so new, practice has actually gotten ahead of theory. We don't totally understand how these minerals form that well, and we definitely don't have modeling tools for them. So I'll talk through where those tools are and some of the ones that we've been working with consultants to develop. And I'm just going to skip ahead here because we know phosphorus is an issue, especially in the Midwest where we have 20% of the world's fresh water. This is both a human health risk as well as an environmental risk due to harmful algal blooms, but also toxic events that kind of induce water scarcity. So to address these concerns, states have been implementing nutrient loss reduction strategies and are at different levels of implementation for nitrogen phosphorus recovery. And so it's definitely a patchwork. We don't have uniform policy, and a lot of people have implemented them. Others are in development. I'm in a state that is in that transitional phase. That's actually provided me an opportunity to be in service of plants that are thinking about decision making. So as JB mentioned in his talk, there's this great synergy between enhanced biological phosphorus removal and then the side stream. So in the mainstream, we have microbes that are taking up that phosphorus and growing under aerobic conditions. They're storing it. And then once that oxygen gets turned off, they re-release it, about 80% of it. And then during digestion, we're also mineralizing proteins. So we have everything we need to drive struvite precipitation. This happens spontaneously if it's a problem. But to address that, people have been installing crystallization systems to control its growth and prevent recirculation of phosphorus. And so there are clear benefits to this, but there's also major challenges that we'll talk through. So first, I'm just going to talk through a study in which we quantify these benefits for a plant near us in the Upper Sangamon watershed of Central Illinois, the sanitary district of Decatur. So this plant has some challenges. It has a combined flow, lots of major storms. It is also essentially a receiving plant for grain processing streams. It has a very low municipal flow, and about 80 to 90% of their phosphorus flow is concentrated streams from corn and soy refineries. And so we got a grant to work with watershed modelers to kind of develop water tools to compare the benefits of nutrient removal and recovery to best management practices. So for one of my colleagues that was working on like this optimization, what he needed was for me to build surrogates. So we went through this process of developing plant-wide models in these simulators that practitioners use to simulate the impacts of chemical removal, business as usual, enhanced biological phosphorus removal with and without struvite precipitation, and then train neural nets to serve as basically proxies of these complex models so that they'd be integrated into an optimization framework. And that allowed us to really rapidly simulate historical performance if these, based on rainwater data and plant flow, how these different scenarios would, how stable they would be, and what would the cost of removal be overall. So we evaluated different plant layouts that I talked about. So currently they're just running activated sludge. The easiest thing that they could do, as Tom was talking about, was add chemicals to remove that phosphorus. So we just, as he mentioned, rather than alum, add ferric chloride to the secondary clarifier to remove that phosphorus. And then we evaluated 2 or 3 different EBPR scenarios. So EBPR based on their current composition, 5-stage Bardenfo process, and then that same process with carbon addition because they have such a high phosphorus load. and then compare that to a side stream recovery scenario. And so we figured out how to train these neural nets. What we needed to do was be able to build this model and then run it 10,000 times to generate enough data to train the neural net. Okay, so that was a major headache for my student. The more complex the model got, the longer it took to run, the more frequently it crashed. But eventually we got our data after a lot of trial and error. And what we can see is, so here first we're looking at effluent, different water quality parameters and plant-based parameters. So in terms of effluent nitrate, business as usual aligns with the historical data. Chemical precipitation doesn't do anything for nitrate, but if we implement this EBPR process that includes an anoxic stage and internal recycles, then we could get the model to really reduce the effluent nitrate as well. The effluent COD was all within similar ranges, but what I'll talk about is that side stream recovery. Because we're reducing that recirculation, there's less biomass growth, so less is leaving the plant as well. And when we look at the spread of data for these different chemical removal processes and biological removal processes, we can see that struvite actually had the least amount of variance as well. It was the most stable process because that return flow, especially when stormwater comes in, can be really challenging for the process to manage when there's no carbon available to take it up. And then from the plant perspective, the other main benefit is that you're reducing solids production as well. If you're taking that phosphorus out as a solid product, then less is going back and less biomass is growing on it in order to remove it. As I mentioned, we train these artificial neural networks with the data, and as you can see, they all train quite well. These are mechanistic models, so they should train well, right? Most of that variance is embedded with the first principles, so the neural net should be able to learn from the relationships between the variables, and that's what we saw. But as the system got more complex, then we did see the R-squared between our simulation data and the plant-wide simulator and the ANN data. We started to see some variability there, but overall quite strong. And so kind of just from the perspective of this community focused on phosphorus sustainability, I like to just kind of simplify things here a bit for a moment. So for these different scenarios, business as usual, we're losing it all out of the plant. If we precipitate, then that is phosphorus being stored in biomass, and it's likely not to be that available. It depends on the iron redox activity and the solubility of the phase, but a lot of times that sludge is not land applied because the phosphorus content is too high. For EBPR, we achieve the same level of removal, and it's in sludge as well. But when we do that side stream precipitation, we can kind of think of the EBPR process as a concentration step, right? So we do this uptake, and then we re-release it in a concentrated stream that allows us to capture it in this concentrated product. So we could potentially recover, based on our modeling, the median value was 60% if everything works well, if all the struvite that forms is recovered, okay? So we can kind of think of this as a way to channel a dilute stream to a valuable product. And so in terms of the benefit, when we ran these long-term modeling scenarios with the ANNs, what we saw is that the most resilient scenario was the EBPR with struvite. Because the plant was handling a lower load, it could tolerate these major storm events much better. And it didn't require a lot of carbon addition. So it was actually one of the cheaper options. You're adding chemicals to drive precipitation, but for this plant in particular, adding it in the side stream at a very specified dose was better than supplementing carbon, which is fairly expensive. So this has these modeling results, are promising, and it reflects this fairly rapid adoption of side stream precipitation. This is a map from the Ostara website. This is the most popular technology that is being used. There are several different technology providers, but so the basic premise is that we take this digestate that has then been dewatered, and we take that liquid fraction after solid-liquid separation. We add magnesium chloride and sodium hydroxide to create conditions to drive precipitation, and we create a lot of turbulence so that we can recover granules, okay? And so this is kind of different than typical wastewater treatment. They're actually trying to generate a fertilizer product that could be blended, okay? So they're not that interested in the overall performance in terms of the plant benefit. The company is trying to generate a really good product that it can sell, okay? And that creates a tension that I'll talk about. So when we model this, the current modeling tools can't really capture the phosphorus that leaves in the treated effluent that isn't captured. Okay, so because we're fluidizing these particles, there's a pretty major risk that small particles that form as nucleates wash out and then redissolve. And that represents chemical loss, basically, right? That it's a lost investment, okay? Lost chemicals, because once we enter, as JB was saying, once it becomes dilute, the struvite's just going to redissolve, and then it has to be taken up again by EBPR. So we've been able to, now that these plants have been operating for some time, we've been able to serve as a resource to get access to data, do the analyses, because we have funding to do it, that utilities and practitioners don't have time to do. And so one of the things that we really want to communicate is, like, people need to think about our key performance indicators a little bit differently. So when they do, when you read papers about struvite or people run pilots, they're really focused on the conversion. So how much of the soluble orthophosphate is being precipitated, okay? And those numbers are great. Struvite is not very soluble, and these are often 90 to 95%. So this is data from one of the plants that has an Ostara reactor in Wisconsin, and you can see that, yeah, generally when we do training time series analysis, that, yeah, the trend can eclipse 80%. They're doing a lot of dilution, so this is a little lower than cases in which you're doing it in batch in the lab, but generally really good conversion. Okay, but when we think about how efficiently that reactor is working in terms of the product that it is recovering and how much it's losing, then what we really need to focus on is this effluent stream relative to the harvest, okay? And so we call this yield, reactor yield, okay? And it represents the ratio of the lost struvite over, or the harvested struvite over the total struvite that's formed, okay? And this doesn't look nearly as good. Here's the same facility, and you can see there was a long learning phase where the majority of struvite they formed was washing out of the reactor, okay? So they had cases at this plant where the effluent of the plant was higher than the influent because of this loss and delayed the redissolution. So they figured out how to do that, and that was a compromise between the utility and the fertilizer company, because the smaller the particle, the more efficient this works, okay? But they want the larger granules are better for reapplication. So they kind of figured out through seeding the reactor, making compromises about the product size, how to get these values higher, and they are, you know, on the median values, kind of having a downward trend. They had a really good period of time, and then they stopped paying as much attention to it. But what you can see is throughout this entire period, there are major upset events that occur, and they don't really understand why. So we've been working with them to understand this. And what happens is they call what they call is a colloidal bloom. Something happens, and there's just this massive formation of nucleates that just all wash out of the reactor. And And so there's some clarification embedded in the top of the reactor to kind of the velocity slows down. They have a weir there, and you can see when you have those major loss events, then it's quite turbid. That's just a wasted product. And this is something that has been seen in the literature as well. And these yields can range from so as high as 85%, but down to 10%. And so the reason for this is that if you break these granules apart, they are just aggregates of very fine particles, right? The main pathway of formation, struvite is a very eager mineral. Once it has a low activation energy barrier because it includes water, and it forms really fast. And our main challenge is not conversion, it's aggregation. Okay, and you can see there are these boundaries where upsets occur, where there's something that really interrupts aggregation. Okay, so in our lab, we're working on trying to understand what kind of molecules influence that, but we're also trying to develop tools that help us just understand the impacts of EBPR. Okay, so on EBPR. So the next study I'll talk through quickly is what happens when we lose these finds. So in that first paper, we were using the simulation tools that assume that all the struvite that's formed is harvested. None of the simulators really capture this impact of fines. So we built a tool to understand, well, if the reactor is operating well, what benefit it provides, and when it's not, what is the impact on the EBPR process? And so from that same plant, we can see that this is roughly like the lost phosphorus on bad months. This red region, you can have pretty much no recovery, and that represents, those are cases in which the return load for this plant is about 30%, up to 25 to 30% of their mainstream. And so the challenge is that most models for these biological processes have been used as templates for struvite growth. And what that means is that they are just characterizing the growth rate based on the mass of struvite in the reactor. And so that's how we can get these high recoveries. But in reality, so this is the driving force, the thermodynamic driving force, and then the mass of struvite. And then if this was an accurate model, then this should be a constant value, the rate constant, right? That's the whole idea. The rate constant is a constant value. But when we tested this model that practitioners use with different masses of the same particle size, what we saw is that, well, it's directly related, the rate constant that we extract based on this model is directly related to sea loading and saturation index. This model doesn't make any sense, unfortunately. You need something that captures surface area. And the challenge there is, well, that they have to characterize surface area. This model fails really badly. So we built a particle size based model for dissolution. We could do that based on recovering product, dissolving it based on size, and establishing a relationship between surface area and the re-release of phosphorus, the dissolution rate, okay? And characterize the impact of yield on the plant effluent, okay? And so just quickly walking you through that experimental and modeling flow, we worked with utilities, collected struvite from multiple reactors, evaluated the area based dissolution, extracted kinetic rate constants that were not constant, but within a range, depended on the material and the location. And then used this model to create a population balance-based model for an existing simulator that we could integrate with. It was a little more flexible than the other. It's called Sumo, which is getting more and more popular due to its flexibility. And so this was quite challenging because we had to create a bunch of different state variables, not just total mass, but size classes. Okay, I don't want to bore everybody, but basically we tracked the particle size over time throughout the plant, okay, from how it was lost to back to ions, okay? And what we found was, well, when we're losing particles in this range below 200 microns, then it's all going to redissolve. Okay, so if it was stable and it went back to primary clarification and was collected, then that would still provide plant benefit. But because this material dissolves really quickly, then it does represent wasted chemicals, right? If the struvite that's lost redissolves, there was no point in forming it in the first place. Okay. And because of that, we see a direct relationship between the yield and the effluent orthopy. Okay. So when the particles are larger, then we do see more of it being in the biosolids. But there's this direct relationship. If we have really great yield, then we can capture most of the orthopy. But if we are oscillating between this or operating down here, then the net benefit is not really there, and the plant effluent is very sensitive to the performance. Okay, so we could see this relationship in the effluent really clearly. The orthopy being nearly linear, inversely related to the yield. So this was a really interesting project. We've been trying to develop the crystallization model, but what we've come to understand is that the parameters that we need, we're not going to be able to get to build that model. So we can understand it in the lab, design reactors that reduce the risk, but probably data-driven tools are going to be the most useful for utilities because they can just learn the dynamics of the reactor without the data that we need for a mechanistic model. All right, so I'll just finish with something a little bit more practical that related to what Tom is talking about. Doing this side stream recovery for a fertilizer product makes sense when you have a really big plant, right? You have some economies of scale. You can generate enough product to make it worth the star's time to pick it up, to transport it, to deal with the hassles of keeping that system running. And so, but the other way that people are starting to do this, which is gaining a lot of steam, is to just immobilize it in the biosolids. So after digestion, where struvite precipitation is really favorable, having a unit operation there before dewatering to just induce it in the solids. And then the risk of losing those fines is much lower because that unit is followed by solid liquid separation, right? So you get the benefit of reducing that return flow, but unfortunately, the opportunity to recover that struvite is much harder because it's embedded in the biosolids, okay? So they're working on doing that recovery, but it's going to be very, very hard. So we've been able to access data from, as I mentioned, I've already shown some of this data for the digestate reactor, in which we're taking that sludge and stripping the phosphorus out before digestion, and then blending it with the centrate to combine it with the ammonia, and then precipitating. That's what's happening at 9 Springs wastewater treatment in Madison, Wisconsin. And then this unit operation is data we got from Metro Denver. Okay. And so I'll just be showing you a quick comparison of these. So I already showed you the conversion. When we're to do this comparison, we're actually like doing a comparison of the influence. So for the struvite reactor or the pearl reactor, we're accounting for dilution from the recirculation line. And so when we do that, then the conversion is actually much lower. So in order to grow those good crystals, they want to keep it like barely super saturated. They want to control growth as much as they can. So it has to be very dilute. So as a result, the conversion is lower, and you see a lot of seasonality that's tied to the EBPR activity. For the biosolids precipitation reactor, they aren't trying to grow a granule, and they have immense conversion, right? They're treating much higher concentrations because it's not just the liquid fraction, and they have a much longer residence time. And so they're consistently observing greater than 90% conversion. And they don't really see much of a seasonal trend, whereas at Nine Springs, we see a lot of oscillation and seasonality. Okay. So in terms of the plant benefit, that key performance indicator for the side stream, as I mentioned, this is the same data, is the yield, and we see, kind of in the range of 50 to 75% with frequent upset events. But when we have that followed by, when we do precipitation in the biosolids matrix, and we have dewatering afterward, then the yield, the sequestration in this case, not the product yield, but the actual capture of the struvite that's formed is significantly higher. So this is something that I see as kind of a challenge, is that in the case of trying to promote recovery, is that it presents a lot of challenges, right? And it doesn't really provide nearly as much benefit to the plant as just inducing struvite precipitation in the biosolids. So I think, recovery will make sense in fewer cases, but I think what this data shows from Denver Metro is that struvite precipitation has a wide-ranging benefit for people, and we can start treating it like a unit operation that we can just kind of easily design around rather than having a really expensive crystallization reactor. So yeah, I'll stop there. So just in conclusion, side stream P removal can really improve EBPR performance and resilience. But the key challenge that we need to pay attention to and potentially have technological interventions for is low reactor yield from the struvite reactors that are already in place. This is something that we really need to address for those utilities. And that I think in general, biosolids precipitation although it may hinder recovery efforts, it has more plant-wide benefits than crystal recovery, unfortunately, in terms of ease of operation and increasing that stability and reducing the variability of that return flow. So it makes the plant a lot easier to operate. All right, so with that, I would just like to thank my group. So Sammy Aguiar, who is an ASU alum, did a lot of the modeling work. Aryan did some plant modeling and is now at Black and Beach, and then Rishabh is doing data-driven analysis. And I have a whole host of utility collaborators and funding agencies. Thanks for your time. Happy to answer any questions.
About 5 minutes. A couple questions. First one's about the comment of when you do the precipitation method in the biosolids, you're not recycling it or recovering it. But if you're land applying, is that P bioavailable? And would you kind of count that as that, or is it so locked up in the metals that it's not really bioavailable?
Yeah, so struvite is plant available if it's in the root zone. So when struvite granules are being blended with MAP or DAP or TSP, they're being basically ejected into the soil along where they're planting. Okay. So if you broadcast it, that fertilizer is not really available because it's so insoluble. Okay. If it is where the roots are going to exude acid, then it is available. Okay. If it's in the biosolids and it's just spread, it is not going. It's not going to be nearly as available. Yeah. It's going to constrain application because you have a lot of phosphorus. Yeah. Right. The benefit of struvite is that you're segregating that phosphorus and concentrating it. Yeah. So in the case of the Madison plant, they probably would still elect to do struvite recovery because they are such a nutrient-constrained watershed. Okay. And they need to export those nutrients from the watershed. That's one of the primary benefits of that system from their perspective. Metro Denver, they're trying to get it out because they want to be able, they generate so many biosolids that they want to recover it and separate the struvite, but they're really struggling. The yields that they expected, that they were promised, they're getting about 5% of that.
Oh my.
So there's been a lot of promises being made that aren't being realized.
Stara?
Initially, like I said, I mean, I think the thing is, like, as I mentioned, practice is getting ahead of knowledge, right?
Yeah.
And so they're learning as they go. So
Okay.
hopefully we'll get those recoveries higher. Just like I showed you in yield, like the Ostara plants when they first came on,
They were low. And
they were kind of negatively impacting the plant,
then,
right? So I think over time we'll get better at it, and that's been nice to be a part of
Okay.
in terms of developing the tools. But I think, yeah, the challenge is that, you know, utilities like you all are, you're thinking about your permit limits,
Yeah.
right?
Yep.
So unless biosolids become so hard to get rid of, you know, based on the P content, then why would segregation be that valuable, right? If you're just really worried about the return flow.
Yeah. And then, oh, go
I was
ahead.
gonna say biosolids with struvite might be more applicable to like a pasture grass or something that
Yeah.
is in a row crop.
Yeah.
Totally.
So it might have more value in those.
That's true. Yeah, it's still recovery. It's just not synthetic fertilizer displacement,
Yeah.
right?
Yeah.
It's not reducing soluble P losses.
Yeah.
Like that's what attracted me to this topic, right?
Yeah.
Yeah.
Jacob?
Oh yeah, Jacob had his hand up initially too.
Yeah, and this could be a very naive question, but those of you that know me know that I'm good at asking those types of questions. So your particle size distribution and your comment about the fines and whatnot got me thinking, to what extent has heterogeneous nucleation been explored for recovery? Yeah, obviously it occurs in the system because it occurs on the walls of pipes, but when you're intentionally recovering it, I just wonder to what extent people have designed using heterogeneous nucleation versus homogeneous.
We've been trying to just understand heterogeneous nucleation. It happens really easily. So if there's a seed there, the surface serves as a nucleation site, but it grows outward, so it's hard to keep on the granule.
Yeah. I mean, those fines form the powder cloud that you saw, right? So we know it homogeneously nucleates. And so there's this control knob you can.
Yes. So that's actually what they are trying to do, is to keep the saturation really low, so that heterogeneous nucleation is the primary pathway. The challenge is that, well, it's hard to distinguish between homogeneous and heterogeneous nucleation. It's true, right?
Seeds.
So when there are no seeds, then we see, you know, a big lag phase and Oswald ripening. But as soon as there's a seed, it's there's no lag phase. It's and we have a burst. Yeah.
Seeds later on.
Yeah.
Thank you.
Yeah. Happy to talk more about that.
Very nice talk and very insightful talk. So I have one question. Precipitate out provide. Do you use any extra ammonia or the ammonia come from?
No, so the ammonia is always in excess. So after digestion, the molar ratio is usually at least 10-1, N to P.
So you need to add the ammonia to do wastewater to precipitate out the struvite, right?
The ammonia is there. No, the ammonia is in excess. You need to add magnesium. That's the chemical additive. So the magnesium ratio, depending on where you are, how hard your water is usually in the range of like 0.3 to 0.7.
No extra ammonia.
No extra ammonia. You only see about 5 to 10% ammonia removal when you do struvite precipitation because of that excess. So people don't even really count the benefit of the nitrogen removal. That's more of a life cycle impact, and agronomic benefit is capturing that nitrogen. But for the plant, it's not significant.
May have missed this. I'm curious about when you do blend struvite biosolids. Does it have effect on dewatering? Did you mention that?
Yeah. So that is, that's one of the benefits I didn't mention, is that when you do the precipitation, as JB was mentioning, the phosphate concentration negatively impacts dewatering. So when you precipitate beforehand, you're taking that phosphate out of solution, and you're also adding magnesium.
Okay.
So it kind of reduces that negative charge density, and the required polymer dose goes way down. So the plant savings are primarily associated with reduced polymer dosing, as well as reducing the return flow of phosphorus. But Denver, so they don't really have much carbon limitation. So it's the polymer dose. They save several $100,000 a month. Yeah. So that's kind of the, oh geez, this isn't what I was hoping to see, but it's actually it's a good process. a little over designed in my opinion, but
One more question?
I'd have one more.
sure.
When you set up all the different plant models to kind of estimate like stability and stuff,
Yeah.
remind me, that was a conventional activated sludge and they did not have any kind of nutrient removal
Correct.
at the point.
Just ammonia oxidation.
Was it hard to like, how did you get to convincing yourself that your model was going to accurately model EBPR?
Oh, yeah. Well, they have a lot of excess tankage
Okay.
because they're a combined flow plant. So what we did was we took their tankage and we created zones.
Oh, cool.
Yeah.
So you were able to kind of like calibrate your model to what they.
Yeah, we had to increase the anaerobic zone a little bit.
Yeah.
But we used their existing clarification and existing aeration basin.
Oh, that's awesome.
Yeah.
That's great.
Yeah.
Because we found it pretty challenging to like get our plant models that consultants have to like match up
Totally.
with our plant.
And it's
like
just
the
the
hardest-
stimulation.
Yeah.
Yeah.
But the fact that you were able to like do some trialing in the field to like get a sense is awesome.
Well, mostly what we did for this model, it wasn't a dynamic model. So we just captured the variability in their data and ran steady state models so that
Nice.
the data, we don't really capture the dynamics, but the variability.
Gotcha. That makes sense.
So mostly what we're concerned with is like, does our simulation space, our box and whisker plots, our variability align with the plant variability?
Yeah, that makes sense.
So we didn't do a sampling campaign, so we didn't have good calibration data
Yeah,
for
yeah.
dynamics, just historical.
What do they have now? Like, did they move forward with one of those?
Well, they're working with a consultant to work on their plan. The big challenge for them is that their influent phosphorus can range from 20 to 70 milligrams per liter. So they're negotiating with their clients to do pretreatment, but basically they have to get it down in your range, like 8 to 10, for EBPR to be feasible. And the consultants that they're working with who are proposing to do biosolids precipitation. So, yeah. Any other questions?
All right, let's think row. I found it.
Oops.
Some backup slides there.
Yeah, back up.
Okay. Our next speaker, you've already heard, if you were here this morning, you heard me, my introduction. Jim, you've introduced me, so you know who I am. I'm Doug Call. I'm a professor here in environmental engineering. And I'm going to talk about something related, but completely different at the same time. What we're going to do is we're going to dive deep into the world of phosphorus accumulating organisms, the PAOs, the ones that are involved in these EBPR systems. It's not just me on this. In fact, I really need to recognize the main driver, Jessica Deaver. She was a postdoc in my group, amazing postdoc. She's now a principal scientist at Hazen and Sawyer. Tom, who's here, also participated. He generously let us use his facility for this study and was extremely helpful in collecting the samples that you're going to hear about. And Amy Grundon here in microbiology, because this got to a level of depth into microbial regulation and things like that that I don't have expertise in. So it was fantastic to have the opportunity to work with her. Okay, so can we use these tools, DNA and RNA sequencing, to learn new things about EBPR? Really, that's what our question was, and in particular, EBPR that experiences upsets. This is kind of cool. This is a TEM image. Actually, Jacob Jones helped collect these images, the analytical instrumentation facility here. This is a section. Basically, we've taken some of the microbes from a wastewater facility, sliced them in half, and then looked at them under a transmission electron microscope. I wanted to put this up here because I want to emphasize that black ball in the middle, that's the polyphosphate. To give you a sense of how much phosphate these microbes can accumulate. On a dry weight basis, they've seen upwards of 15%. That is a lot. Typically, coli is 1 to 2%. So these are extremely unique microbes. One of the main drivers for this was early on when STEPS was getting started, we were talking to wastewater facilities, and we said, hey, how's your biological process working for phosphorus removal? And lots of times it would be followed by, well, we like it when it works, but it often doesn't work. And so we started talking with more and more facilities, and just in this region alone, about half of the facilities we talked to said they'll experience these upsets in phosphorus removal. And sometimes they didn't even know reasons why. Some of them did, but a lot of them said, we don't really know. It gets hot and it messes up. It gets cold and it messes up. And so there was no real consistency. So STEPS did a national survey and got some really nice quotes here that are consistent with what we saw regionally. Operators saying the bugs you think they're going to work, and for reasons that are completely mysterious, they decide one day to stop working. You got this working population who really think they can do great, but we have no clue as to what they need to be happy. So this seemed like an opportunity to learn more about why we might be experiencing these upsets from a fundamental microbial perspective. I'm not going to spend a lot of time on this because we've already heard this from the previous speakers. But basically, in a very generic sense, we need to have the right conditions, right? And what we think are the right conditions are this anaerobic zone, get some carbon in there, followed by an aerobic zone, right? So very generic layout there. And we've heard about what the microbes do in those two zones, but I really want you to focus on this fact that it's a cycling, right? It's a cycling process for these microbes. They're continuously going through this process where on one stage, the anaerobic, they are taking up carbon and forming it into polyhydroxyalkanoates. They're breaking apart glycogen and polyphosphate, and so that's why you get that release. Throw them into the aerobic zone, and it's just the reverse. The polyhydroxyalkanoate broken down, you rebuild your glycogen, and then you take up the phosphate and build that big black ball that was in that picture on the first slide of polyphosphate. So it's this continuous cycle that's going on. And sure, we can go and measure in a facility. We can measure the carbon, we can measure the phosphorus, and we can see these things going up and down. But there's another thing that we can do to gain deeper insight into not only the cycling, but specifically what things are being cycled at different times. How do we do this? That's where the tools of DNA and RNA sequencing come into play. So DNA, we've all got it, and all the microbes have it too. That's our blueprint. That's all the genes that we have, right? That tell us the things that we could be making, right? Same with the microbes. It's got a whole blueprint of the different enzymes and things that they could be making. RNA is transcribed from the DNA. So when the microbe says, oh, there's a bunch of phosphorus here, I better make an enzyme that can help me with that phosphorus, it transcribes the DNA into RNA that then would be turned into that protein that could be used to help with the phosphorus removal. So that's the connection. And really why we're interested in RNA is because it gets us closer to understanding what the microbes are possibly doing. Notice I said possibly doing, because there's a whole nother discussion we could have about regulation of enzymes and proteins, where even though you make the protein, the cell might actually shut it down. We'll leave that off the discussion for now, but the point of RNA is it gets us pretty close to understanding what these microbes might be doing. So what we did is metagenomics and metatranscriptomics, which is basically sequencing all of the DNA from a sample and sequencing all of the RNA from that same sample. My postdoc came up with this, so Jessica came up with this analogy to help people understand what we mean by metagenomics in this sequencing process, and I just had to include it. Basically, her analogy is, imagine if I asked you to put together 4 puzzles, but what I'm going to do is I'm going to take all of the pieces and put them in one huge pile. That's basically what metagenomics is we've got all the DNA here, and what we have to do is put it all back together to make 4 different microorganisms. That's metagenomics. Okay, so let's talk a little bit first, though, about the microbes that do this process. And what has been done? What do we already know in terms of using sequencing to answer some of these questions about phosphorus removal? There has been a lot of DNA sequencing of PAO communities around the world. Full-scale facilities, multiple years. We have basically figured out at this point that there are three main genera that are doing all the work. It's either Accumulobacter, it's either Azonexus, which used to be called Dichloromonas, and now it's Phosphorobacter instead of Tetrasphaera. So you heard some people saying Tetrasphaera earlier. That's now been changed to Phosphorobacter. Those are the big three that we consistently find all across the world. There are some other ones that will also do some phosphorus uptake, but they don't necessarily cycle it like these other microbes. And so really what the key players are associated with those genera. The cyclical aspect that I mentioned about what they do, this has been shown. So for example, here, this is looking at Accumulobacter, cyclical gene expression. And so what you're looking at on the y-axis of all these little images up here is that's the expression level of genes associated with different things. So like aerobic metabolisms, when there's low phosphorus, when there's high phosphorus. And the gray zone is the anaerobic stage. And then right next to that is the aerobic stage. And so you can clearly see there's these cyclical patterns in the gene expression of this microorganism as it's transitioning from the anaerobic to the aerobic phase. But what's wrapped up inside all of this here is those different genes. What are they doing? What are they associated with? So this has been done with stable microbial communities, either with the lab scale. So this is Trina McMahon's lab in Wisconsin, has done this with a enriched culture of Accumulobacter. But then other groups have done this at full-scale facilities, but they all had stable operation. And so what we wanted to figure out is, could these tools give us insight into what happens during unstable operation or an instability event when the biological process is having trouble removing phosphorus? So that's where Tom comes in, and we said, hey, Tom, well, we really like to do a project and use your facility because oftentimes they have an instability event during the winter season. So we went ahead and said, well, let's just set this up. Maybe they will have it, maybe they won't. So we started doing a sampling campaign at their facility. So it's about a 15 to 20 milligram per day facility. They have an A2O process, so anaerobic, anoxic, aerobic, for combined nitrogen phosphorus removal. Their SRT is about 10 days. And then as needed, as he mentioned, sometimes they'll put in some supplemental carbon. The other thing to note here is they have parallel process trains. And that was wonderful because we could sample from both and have replicates for this process, which is great that we could have that. It's very difficult many times to get replicates in full-scale systems. And then the sampling locations, A, B, C, D, E, and G, these are different sampling locations of where we grab samples. Okay, so luckily for us, unlucky for Tom, there was an instability event. So this is back at the end of 2023, the yellow stars. This is where we were collecting samples. And we got one before, right in the middle, and then a little bit after. Timing was spot on. What's to note here is that's the effluent TP coming out. So while that goes down, I believe they turned on alum to help bring that effluent TP down. The biological process was still having issues. So that yellow star in the middle really was when the instability event was still occurring. So we took these samples and next did our metagenomics and metatranscriptomics. Before I get into those results, though, I want to mention we also looked at a lot of the process performance data that Tom shared with us to see, could we see a clear connection between other things in this upset event? And honestly, of the data that we have, we don't really see anything. So for example, influent phosphorus during the instability event, I don't know if you can see the gray in there. Can you see the gray? Oh, it's highlighted on my screen. Anyways, there's a gray bar right around the dates. Look towards the end of November. Influent phosphorus didn't really change much before and during that period. The mixed liquor suspended solids Didn't really change much. Ammonia concentration, not much going on there. We looked at the BOD to total phosphorus ratio, which the guidance has always been try to be somewhere around 20 to 30 for stable EBPR. And we're kind of around that, around 20 to 30 throughout this whole time. So we didn't really see much changing in these kinds of parameters. We did notice it got colder, and I'll talk a little bit about that later. So there was a big temperature drop right around the time of this. Okay. So let's talk about, first of all, the DNA sequencing results. So what we do is we take all that DNA and we try to rebuild the genomes. So they're called MAGs. They're metagenomic assembled genomes. And when we've assembled these, we can now begin to identify them using existing databases. So this is looking at before, during, and after that instability event. So those 3 sample times. And this is looking all across the genre that we collected that I think we're below. I think our cutoff was maybe 5% relative abundance. And so really you're just looking at the major players that were present. What I want to highlight here is that the one on the bottom, Acuminobacter, is really one of the biggest. It's about 6% relative abundance. That is a known PAO. Azonexus up there as well too. That was the other major genus of PAO that we found. So we dug a little bit deeper. Now let's just look at the PAOs. So forget about all the other microbes. Before, during, after. And what you notice is all those A's, those are all Acuminobacters, but they're different species. So anything from Phosphitis to Propicinus and so on. Those are different species, and we're able to get that species resolution because we've got most of the genome intact, right? And then the Azonexus in there as well. So we had to make a decision now. What do we focus in on when we look at the RNA, when we map the RNA to these MAGs? And since the Azonexus, those 2 orange species really seemed like they were the highest relative abundance, we just focused on those 2 and looked at their expression levels of RNA. Before I say that, though, one thing that also confirmed, not just based on relative abundance, but looked at transcript abundance. So now you're looking at the abundance of the RNA transcripts. These have all been normalized so we can have a more fair comparison across samples that we've sequenced. And basically, you see the same story. Before, during, and after, these orange ones associated with these 2 Acuminobacter species really are making up most of the transcripts that we're seeing within the PAO communities. So that was, again, further support that these are likely the 2 major players in this system. So we focused on these. Now, when you look at these, you see transcript abundance, right? So it's how much RNA that we recover, right, for specific genes. But I can't tell you what genes they are, right? I can just tell you there's a lot of RNA and we got it from these different microbes. So one way for us to look at whether or not these microbes were changing their different expression levels of certain genes is to do these things called volcano plots. What is a volcano plot? So a couple things here. On the y-axis, this is log2 fold change. Basically allows us to see when you have a gene and it changes its expression level by doubling, by tripling, by quadrupling, the farther out you go, the more of fold change that you have. On the y-axis, this is the negative log of your p-value. So this is a statistical test. And so the higher up you go, the more significant that change is. If you're down really low, there's probably just a lot of noise, there's a lot of randomness, and so it's not a significant difference. So if you are out on the sides and up really high, it's both a very large change in the gene expression and it's a significant difference. So these allow us to very quickly visually see differences at different time points. Okay, so either significantly expressed, log fold changes, and the way we set this up is we've got this case anaerobic versus the aerobic location. If everything goes to the right, anything in that direction means we have higher expression in the anaerobic zone relative to the aerobic zone. So let's zoom through these and look at the volcano plots for stable versus unstable conditions. So this is now comparing the anaerobic versus the anaerobic anoxic phase. And what you notice is the volcano plot looks much different when things are stable versus unstable. Move over. Now we're talking anoxic versus aerobic. That's a huge difference in the amount of significantly expressed genes. And then look now at anaerobic versus aerobic. Completely different. And so here's all of them shown on one graph. Basically, what we are seeing here is that they are shifting the expression of all of the genes down one basin. So everything under stable conditions that they were doing in the anaerobic basin, they're now doing in the anoxic basin. And then they push the anoxic activity over to the aerobic. And so it makes sense that if you're delaying all of your activity associated with stable operation, you might get an increase in the release of phosphorus when you're unstable. What exactly are they expressing? I am not going to dive deep into this because this is where you get down to specific gene levels, right? And say this gene does this gene does that. All I want to say here is the biggest differences we saw were genes involved in carbon storage. So remember the cycling? So here, everything to the right of that dotted line is expressed most in the anaerobic zone when the stable operation, or in the anoxic zone in the unstable operation. So basically, you can see everything is shifting over to that anoxic zone during the unstable phase. Genes involved in carbon storage, denitrification activity ticked up, and then genes involved in energy production. All those genes that we talked about in the beginning associated with cycling. Okay, so wrap this up. What does this mean? Well, one, we actually just ended up getting more questions than answers, for one, because all we touched on here was really 2 of those Accumulobacter mags that we recovered, right? There's still a lot of other microbes that we can be looking at. The other thing, too, is we don't have data on things like dissolved oxygen, which we think played a really important role here. Our hypothesis is that the depth of the anaerobic zones weren't sufficient anymore. And this could be due potentially to the colder water temperatures. Oxygen more readily dissolves when it's colder. Perhaps the depth of that anaerobic condition just wasn't as deep as it was before when it was warmer. That's a guess, right? But that could cause a potential shift in these gene patterns to kind of kick the activity farther down. All right, I know I'm out of time. Again, thanks for, this is supported by STEPS and largely driven by Jessica Deaver, the postdoc, along with a whole bunch of other people, undergrads and supporters of this work. All right, 1 minute to spare. I'll take questions. Sure, yeah.
I just want to know, like, what is the time scale of the bacteria, the microbes, lifespan of the microbes? So,
the lifespan?
Yeah.
Well, I mean, I would go based on the SRT, right? So the solid retention time in the facility. And this one's about 10 days. So they are moving around in 10 days, cycling across these different basins. Now, how long could one of these microbes last? I don't know. That's a really good question. I mean, a lot of these facilities are operating continuously throughout the year. I don't know.
So what do you call it? Changes in the gene expression, what do you call it? Is it adaptation or evolution of the bacteria?
No, it's not evolution. What it is microbes are constantly needing different things from the blueprint, their DNA, right? So you give them a pizza to eat, they got to make the fork and knife, right? You give them soup to eat, they got to quickly make a spoon, right? And so they're constantly turning on and trying to make the things that they need, the different proteins, whether they're structural or enzymatic. So it's not an evolutionary change. It's just them turning the things on to make the things they need.
So it's like adaptation.
Yeah, in a sense, but without any change to their DNA, right? They're not changing that.
Physiology.
Yes. Question? Yeah.
Right.
So I have a question about microbe communicate or produce the biphosphate inside the vacuum, right?
Yeah.
So my question is that possible to interfere genetically modified size of the vacuum in order to increase accumulation? So,
I think it could be attempted, right? Like we have a good understanding of how they polymerize and make these polyphosphate molecules. So if you can, one, crank up those enzymes that do that, but two, also turn down the things that tell it to stop making it, you might be able to make it bigger, but you're also going to run into the issue of you got to have other stuff. You got to have DNA, you got to have ribosomes, you got to have all the other stuff that the cell needs. So it might be possible to make them bigger than what they do naturally.
because for our process, we involve the yeast bakeries to accumulate polyphosphate, and we capacity to accumulate that polyphosphate is 28%. So I'm wondering if we can interpret genetically to modify that vacuole in terms to more bakeries.
Yeah, I think certainly. I mean, I think you can play around with some gene editing to, we have a really good understanding of what's involved and how they make this. And so, yeah, you can play around, turn things up, turn things down. But I think you'll find that they'll start to do things you didn't expect to try to shut it down.
Thank you, Doug. Thank you all for coming.